Okay, here goes. First thing we're going to talk about today is the Pythagorean theorem. And as you may or may not know, um, this is named for an ancient Greek mathematician named Pythagoras. And he ran a school in Athens. And the way that things worked back then, and in some ways, the way they work now, as far as intellectual property goes, it could have been Pythagoras that came up with this idea. It could have been one of his students at his school that came up with his idea. But since they were a part of his school, the Pythagorean school, then it got named for that school. The Pythagorean theorem came from the Pythagorean school. We can't be 100% sure that Pythagoras is the first one to discover it, but maybe. We also know from some Babylonian tablets, which you might remember from Math 122, the Babylonian number system, that they were aware of the Pythagorean theorem a long time before the Greeks wrote it down. So this was something that wasn't necessarily completely unique to the Greeks, but as far as their world was concerned, they had no idea that anyone else knew about it, so it was a discovery for them. Same thing would be true for the Babylonians. When we talk about the Pythagorean theorem, it's important to note that the Pythagorean theorem works with right triangles. So the Pythagorean theorem only works when we have a right triangle. And when we have a right triangle, we have components, pieces, that sort of has an anatomy, if you will. The longest side of a right triangle, which is the side that is across from the 90-degree angle, which if you think about that, it kind of makes sense. The bigger the angle, the bigger the side across from it's going to be. And so the side that's across from the right angle, the biggest side in the triangle, is called the hypotenuse. And then the other two sides in the triangle are just called legs. We don't really distinguish between those. They're legs, and the other one is the hypotenuse. You may be familiar with the Pythagorean theorem already as a squared plus b squared equals c squared. And I'm not opposed to that. I don't have anything against that. But there is a little bit of danger you should be aware of with a squared plus b squared equals c squared. And that is that this only works if your legs are a and b and your hypotenuse is c. Since those are variables, if I wanted to, I could call a hypotenuse a and this leg b and this leg c. There's nothing wrong with that. They're just variables. I can put them wherever I want. And if I were to label my sides that way, now this doesn't work anymore. So a squared plus b squared plus c squared is great as long as you've labeled your triangle in a specific way. To avoid that issue, I prefer leg squared plus leg squared equals hypotenuse squared. I just think it's a little safer to go leg squared plus leg squared is hypotenuse squared, because now it doesn't matter what variables you use. Leg squared plus leg squared is hypotenuse squared. And that's what we're going to use for our Pythagorean theorem. What this does for us is allows us to be in a situation where if we know two of the three sides of a right triangle, we can find the third side. Let's take a look at how that works. Find the length of the hypotenuse in the right triangle below. So we can see this is a right triangle, and we know two of the three sides. We're looking for the third side. When that's the case, when we have a right triangle, we know two of the three sides, we can use Pythagorean theorem, which is leg squared plus leg squared is hypotenuse squared. And so let's put some numbers in here and see how this works out. So when I put numbers in, I'll have leg squared. Doesn't matter which leg we put first. I'll go ahead and do the 6. And the other leg is 8. And the thing that I'm looking for here is the hypotenuse. So I have 6 squared plus 8 squared is hypotenuse squared. Now I've got an equation that I'm going to solve. And as you all know, we don't do a ton of algebra in here. I suppose this is a little bit. We do have to remember order of operations. Exponents go before addition. the two operations we have over here on the left, or we're going to have to raise numbers to powers. That's exponents, and we have addition. Exponents go before addition, so we'll simplify those exponents. 6 squared plus 8 squared is hypotenuse squared. Now I can add those. 36 and 64 is 100, is hypotenuse squared. And here's a question for you. I want to know how long the hypotenuse is, but right now I have hypotenuse squared. I need to make that squaring go away. Does anybody remember or know what we need to do? Perfect, Zara. Thank you very much. We're going to take the square root of both sides. I'm going to take the square root on the right-hand side because what squaring does, squaring cancels out, or excuse me, square rooting cancels out squaring. So I'm going to take the square root on the right, and that's going to leave me with just hypotenuse. And if I take the square root of the right, we're going to take the square root of the left, and square root of 100 is 10. Some of you who may have had algebra recently, or maybe really strong in algebra, are like, well, wait a minute, the square root of 100, shouldn't that be plus or minus 10? Because positive 10 times positive 10 would give me 100, and negative 10 times negative 10 would also give me 100. And you would be exactly right in a theoretical sense. Here, we're talking about the length of a side of a triangle. And since length, a distance, is always going to be positive, in this case, we can disregard the negative root and just use the positive root and say the hypotenuse is 10. So we're going to be focused on positive roots because we're talking about distances. Are there any questions on this before I have you try one? Excellent. Here goes. Find the length of the hypotenuse in the right triangle below. Round your answer to the nearest hundredth. I'm going to set up a poll for this, and we'll see how we're doing with Pythagorean theorem. And this is definitely a type of question you could expect to see in practice problems, on a quiz, on an exam, just using the Pythagorean theorem. So we're setting up a Pythagorean theorem problem, solving that Pythagorean problem. Let's go another 30 seconds and we'll talk about this one. All right, let's see how we're doing. Okay, really strong agreement. And I think I recognize the other answers. I recognize what happened in those. So let's take a look at this one. So find the length of the hypotenuse in the right triangle below. Round your answer to the nearest hundred. So right triangle, we know 2 of the 3 sides. So we are going to use Pythagorean theorem. In this case, I can plug those legs in and have 7 squared plus 12 squared is hypotenuse squared. And so that's 49 plus 144 is my hypotenuse squared. And let's see there. 49 plus 144 is 193 is hypotenuse squared. We're close, but we're not quite done yet. We don't have the hypotenuse yet. Right now, what we have is the length of the hypotenuse if we were to square it. We've got to do one more step to get the hypotenuse by itself, so we're going to square root the right and square root the left. On the right-hand side, those cancel, leaving hypotenuse. On the left-hand side, we'll take the square root of 193. You have to make sure you find that button on your calculator okay. You should see a button that looks like this for square root. It might have a little 2 up there for square root. So that's the button you'll use to take the square root of 193. And when you do that, let's see here, 193 square root, I get 13.89. And so the length of our hypotenuse here is 13.89. One of the things you can use as sort of a little built-in check that, wait a minute, did I forget to do this last step? Remember the triangle inequality from Tuesday. If I were to try to say that this hypotenuse had a length of 193, well, these 2 sides have to add up to be bigger than the third side. And 7 plus 12 is not bigger than 193. So with those 3 values, I couldn't make a triangle. So this is no good. And wait a minute, there's that one more step I need to do. And that's how we'll get 13.89. Oh, that's true. Hopefully, it could just be that you hit the button wrong. I can tell you, Caroline, when I first hit it on mine, I hit it twice and got 3 point something, and I'm like, no, that can't be right. So because of the same reason, the triangle inequality says that's no good, and it's got to be the longest of the 3 sides. So yeah, very good. Sometimes we just hit the button wrong, and so I would say on a quiz or an exam, maybe if you have enough time, do it twice. Make sure you get the right number there, get the same number both times, and then you can be really confident, because it is easy to hit a button wrong, for sure. Any questions about what we did here before we look at something that's different but very similar? All right. Find the length of the missing leg in the right triangle below. And we're going to round this answer to the nearest tenth. And we can see that we have a right triangle. We know 2 of the 3 sides, so we're going to use Pythagorean theorem. But this time, I already know the hypotenuse. I know one of the legs. I don't know the other leg. We could leave it as just leg, but I don't know. I don't know what it is. I'm looking for it. I'll just call it x. And now I can set up my equation to be leg squared plus the other leg squared is the hypotenuse squared. I want to make sure we're careful that we're putting the things in the right places. That hypotenuse needs to be over there by itself. And so that'll give us x squared plus 64 is whatever 14 squared is, 196. And this is where this gets a little bit different from before. Previously, I knew both numbers on the left-hand side, so I could go ahead and simplify and then add those. Here in this one, I need to get x by itself, so I need to get x squared by itself. So as I look at the left side of the equation here, I need to peel it from the outside in. I need to get rid of that 64 first. When I do that, I'll have the x squared by itself, and then I can finish. To get rid of that 64, what am I going to do to both sides? Yes, that's exactly right, Genesis. You're exactly right. Yes, Zara. Yes, Emily. Very good. I like it when you all chime in. It makes me feel like everybody's right here with us. That's perfect. Yeah, we're going to subtract 64 on the left, because the reason we do that is when we subtract 64 on the left, this positive 64 and negative 64 cancel each other out, leaving us with x squared. Of course, if we subtract 64 on the left, we also have to subtract 64 on the right. And when we do that, we get 132. So x squared is 132. And now we're at a place we're pretty comfortable with at this point. I've got x squared. I want to have x. So I'm going to take the square root of the left and the square root of the right. On the left, the squaring and square root cancel each other out. On the right, I get whatever the square root of 132 is, 11.489125. This problem told me to round to the nearest tenth, so that's what we'll do. We'll find the 10th place, we'll look one space to the right. That's 5 or bigger, so we round up to 11.5. And so what that means is that this other leg that we didn't know has a length of 11.5. That works great with the triangle inequality, because 8 plus 11.5 is bigger than 14, so we're good there. It doesn't tell us the 11.5 is correct, but it can be a way to help us identify a wrong answer. So that's really good. Are there any questions about this before I have you try one? Okay, here goes. Find the missing leg of a right triangle with one leg 12 feet long and a hypotenuse of 22 feet. Round your answer to the nearest hundredth. I'm going to set up a poll for this, and one thing that's different is this time we don't have a picture. You don't have to draw a picture to solve it, although in most cases I think it's a really good idea. So with that in mind, I'll set up the poll here and let you answer this one. And we'll go another 30 seconds and then do this one together. If you need a little more time than that, you can just let me know. All right, let's see where we are on this one. Okay, strong agreement, not quite unanimous, but awfully close. Let's go back and take a look at it together. So in this particular case, you don't have to draw a picture, but I always will draw a picture because it just sort of helps me frame it. So I've got my picture, and let's see, one leg is 12 feet long, and the hypotenuse is 22 feet, and I'm looking for the length of the other leg. Using Pythagorean theorem here, I'll have 12 squared plus x squared is 22 squared. It doesn't matter if you put the 12 squared first or the x squared first, because you know the commutative property lets us add those in any order. We could rearrange them if we wanted to. We'll go ahead and square that. 144 plus x squared is whatever 22 squared is. 484. And just like we saw a minute ago, I'm trying to get x by itself. So I need to get the term that has x in it by itself. So as I look at the left-hand side, I need to peel it from the outside in. I need to get rid of that 144 first. So we'll subtract 144 from the left and the right. On the left-hand side, those 144s cancel each other out, leave an x squared. On the right-hand side, we subtract, and x squared is 340. So we're getting close. Now I just need to do one more step to get x by itself, and this is the part where we're going to square it on the left and square it on the right. Square it on the left, square root and squaring cancel each other out, and the square root of 340, rounded to the nearest hundredth, since that's what the problem asked me to do, will be 18.44. If you want to see the rounding, just let me know and we'll do it. I think most of you are pretty comfortable with rounding at this point, but it's absolutely fine to ask about it if you want to see how we arrived at 18.44. And so that would be the length of this side. I'm going to have you try another Pythagorean theorem question that's a little bit different. You might see this as a trick question, but we're doing it together and we're going to talk about it. So I don't think I'm going to allow you to call it a trick question anymore. What this one says is find the perimeter of a right triangle with one leg 12 feet long and a hypotenuse of 15 feet. So we're told a bunch of things here. We're told we have a right triangle. We know what one of the legs is. We know what the hypotenuse is. So I can use Pythagorean theorem to find the other leg. We just did that. But this question didn't ask what's the length of the other leg. What it said is, what is the perimeter of that right triangle? And just a reminder, when we're talking about perimeter of a right triangle, what we're talking about is the distance around the entire figure. So that's the perimeter. So for perimeter, imagine myself standing up here and walking around the whole thing. How far would I have gone? That's the perimeter of this right triangle. And that's what I want you to find here. Find the perimeter of a right triangle with one leg 12 feet long and a hypotenuse of 15 feet. I'm going to set up a poll for this and let you try this one too. We'll go another 30 seconds and then do this one together. See where we are? Oh, almost unanimous. Outstanding. That's really good. All right, I feel confident about our Pythagorean theorem skills. So let's take a look at this one. We have this right triangle over here, and we know that one leg is 12, the hypotenuse is 15, and since we were asked for the perimeter, we're going to need to know all three sides. So I need to find that third side, and we'll set up our Pythagorean theorem here. X squared plus 12 squared is 15 squared. So x squared plus 144 is equal to 225. I've got to solve this equation for x. And like we've done in the past, when I have that x squared term I need to get by itself, we're going to subtract 144 from both sides. When I subtract 144 on the left, those cancel, leaving just x squared. And when I subtract 144 on the right, I get 81. Taking the square root of both sides to get x by itself, what we end up with is a nice tidy 9. We found out that x is 9, and that's great. We found the missing side length over here. This is 9. Question asks me for the perimeter, though. So what I've got to find is the perimeter, and that's what I get when I add up all three sides. We'll do 15 plus 12 plus 9 to be our perimeter. And let's see, 15 plus 12 plus 9 is 36. It would be 36 feet, but you would just respond with the 36. There's so many different ways you can type feet that it's better if Canvas doesn't have to grade the units. So we would just go with the 36. That's our discussion of the Pythagorean theorem and how we'll use it. Are there any questions about anything we've done up to this point before we go forward onto a new topic? Excellent. Thanks, Nicole. That's helpful for me. All right. Up next is the distance formula. And while I'd like to say, okay, we're all done with Pythagorean theorem, it's not entirely true. If we were given a question where we want to find the distance between the points 1, 3, and 5, 6, so essentially I've just got this point right here that's 1, 3, and this point right here that's 5, 6. And we don't do a ton of graphing, but 1, 3 means 1 on the x-axis and then 3 on the y-axis. 5, 6 means go 5 on the x-axis and then 6 on the y-axis. Just as a reminder, we don't do a ton of graphing, but this is our x-axis and this is our y-axis over here. If I wanted to know how far is it between those 2 points, and that's a little clumsy, right? I mean, I could use a ruler, I guess, but that's not going to be very exact. So instead, what we'll do, what our approach is to find the distance between those 2 points, is we're going to go ahead and draw in a right triangle. And now that distance that we're looking for is the hypotenuse of my right triangle. And I have those 2 legs. And as I look at these 2 legs, I've got this leg over here and I've got this leg over here. And so, if I wanted to find out that hypotenuse, I could say Pythagorean theorem, which is leg squared plus leg squared is hypotenuse squared. Very comfortable with that at this point. Okay. And then, okay, let's say I didn't have any numbers at all, and I just wanted to go from here right to the hypotenuse. Okay, well, I could take the square to the right and the square to the left, and these would cancel. And this is a little clumsy, and it makes me a little bit uncomfortable, and it's okay. We're just kind of developing something right now. I'm not going to ask you to recreate this. Now what I've got is the square root of leg squared plus leg squared, and that's how I would find by hypotenuse. So this hypotenuse here, this distance between those 2 points, the hypotenuse, I could find by doing leg squared plus leg squared and take the square root of it. Okay, well, let's look at these legs in our triangle over here. And again, I'm not going to ask you to recreate this. We're just kind of building up to something right now. So hang in there with me. So if I look at this leg down here, just this one, this goes from some point over here that, I can see it's a 5. That's some x value. And then over here, I also have some x value. And because this one's bigger, I'm going to call it x2, and that one's smaller, I'm going to call it x1. So this one over here on the right, I'm going to call x2, and this one over here on the left, I'm going to call x1. So for this leg right here, the distance from this point to this point is really just the difference between these two numbers. I mean, in the one right here, we can see that it's 5 and 1, so it'd be a distance of 4. But let's just say we didn't have numbers yet, and it's from x2 to x1, we want that difference. All right, so let's write that down. That's from x2 minus x1. That would be how far it is from x1 to x2. That would be the length of this leg right here. Let me know if it's, completely confusing. But this distance from here to here is just whatever x2 is minus whatever x1 is. And then we're going to do the same thing with the y values. When I look at the vertical leg here, this distance, well, okay, I'm going to call this y2 and this y1, and the distance between those, the difference. In this case, that would be this 6 and a 3 would be the y values. If we want to know how long is this leg, we would just subtract those. And so that's going to be y2 minus y1. That's the distance on that leg. And then combining the idea that, okay, if I do some subtraction, I can find out how long this leg is. And if I do some subtraction, I can find out how long this leg is. And if I know the length of those two legs, I can use Pythagorean theorem here to figure out the length of the hypotenuse. Taking all that together, if I want the length of the hypotenuse, this is the formula I would use. And so as it turns out, that thing in that yellow box right there, that is our distance formula. If we want to find the distance between any 2 points, the formula we're going to use is right there. What you'll need to do is be able to use this formula to find the distance between 2 points. I'm not going to ask you to tell me where the formula came from. Do I want you to have an idea where the formula came from? That it's basically the Pythagorean theorem just written in a different way? Yeah, that'd be great. But really, I'm going to ask you to find the distance between 2 points using this formula right here. That's what we're going to do here on this slide. Before I wipe anything out, I'm just going to give you a heads up that I'm going to erase all of this, put the formula up there at the top, and then we're going to find the distance between those 2 points. All right, now we're back to square one. What we found out was the distance formula. The distance between any 2 points, that distance is the square root of x2 minus x1 squared plus y2 minus y1 squared. So that's our distance formula that we're going to use to find the distance between any 2 points. We've been given these 2 points right here, so that's what we're going to use. We don't necessarily have to use a picture for this, but we can. And the key here is you can, if you want to call this one point number 1, so that this is x1 and this is y1, and this point number 2, so that this is x2 and y2, that's just fine. If you want to name them the other way, that's okay too. Just make sure that your x1 and your y1 are together, your x2 and your y2 are together. You can't mix and match those. What I mean by that is, and don't ever do this. We can't say that we're going to call this x1 and this y2. We will not do that ever. If we decide that that's going to be x1, then its partner has to be y1. And then over here in the other one, we'll have x2 and y2. You could switch them, but if you switch them, you got to switch them both. I hope that makes sense, that the ones have to go together, the twos have to go together. Now let's plug this in and see how it plays out. So square root of, all right, let's see, x2 minus x1. So here that'll be 5 minus 1 squared. And then y2 minus y1 will be 6 minus 3. When we simplify here, order of operations still holds. We're going to start inside the parentheses. If we ever have work to do inside parentheses, that's what we're going to do first. So we'll have 5 minus 1 is going to be 4 squared, and 6 minus 3 is going to be 3 squared. If you're thinking, after you've done the subtraction, do you still need the parentheses? And it's an excellent question. We are going to keep those parentheses because there are going to be times when we end up with a negative number inside there, and we want to make sure that we're squaring everything that's inside those parentheses. So I'm going to leave the parentheses there until after I've done my squaring. Continuing our simplifying, the next thing we'll do is we'll do the exponents. And we'll have, let's see, 4 squared is 16, plus 3 squared is 9. Now we'll do the adding and have square root of 25. And the last thing we'll do is the square rooting. So we'll do all the stuff underneath the radical, and the last thing we're going to do is take the square root. And the square root of that 25 will be 5. Our job here was to find the distance between those 2 points, and the distance between those 2 points is 5. That's what we just found. Sort of incidentally, we also found out that the distance between the x's was 4, and the distance between the y's was 3. But what we were really after here was the distance between those 2 points, the hypotenuse of the triangle, which was 5. Are there questions about how to use the distance formula to find the distance between 2 points before I have you try one? Okay, here goes. Be careful. I dropped a negative in this one. Find the distance between the points 8, -1 and 4, 2. Be careful with that negative. It may give you a little trouble. We'll talk about it when we get there. I guess if we need to. So the distance between those 2 points. We'll go another 20 seconds. If that's not enough time, you let me know, and we'll talk about it. Okay, let's see where we are. Not quite unanimous, but really close. That's usually where we land, and that's a good place for us to be. If you see something that doesn't make sense, make sure you ask about it. Let's take a look at this one. You don't have to draw a picture, although you can. I'm going to go ahead and just call this x1, y1, and this x2, y2. You could do it the other way, but I'll go ahead and do it this way. You know what? I'm going to do it the other way to prove that you can do it either way. I'm going to call this one x2, y2, and this one x1, y1, because that's probably not what most of you did, and I want you to see that you can name them either way. So we'll do it that way. The distance here is going to be the square root of, all right, so x2 minus x1, so that's 8 minus 4 squared. And then y2 minus y1 is negative 1 minus 2 squared. Be careful with negatives on these. I don't think the formula is going to be hard, but the negatives can trip you up sometimes. And then let's see, that gives me 4 squared plus negative 1 minus 2 is negative 3 squared. Before I go forward, I'm going to take a little detour here just for a second to remind you of something from algebra. Whenever we have parentheses around something that's squared, that's different than if we don't have parentheses around something squared. When we use the distance formula, it's going to be this one right here. So there shouldn't be any confusion as far as which one is this. But just sort of a reminder from algebra that when we don't have parentheses, the only thing getting squared here is the 3. And then the negative sign just comes along for the ride. So this would be negative 9. The 3 gets squared, the negative comes along for the ride. What we have here in the distance formula, the reason we'll keep those parentheses is because we're squaring everything inside the parentheses. That's what those parentheses tell us to do. So this is negative 3 multiplied by negative 3, which is positive 9. We want it to be positive. Remember, we're talking about a distance between 2 points here. So we want to end up with a positive number after we square. That's just a little bit of a side note there real quick that we're squaring everything. Oops. We are squaring everything inside the parentheses so that negative 3 times negative 3 ends up with a positive 9. All right. As we keep going then, we'll have 4 squared is 16 plus 3 squared is 9. That'll be the square root of 25, which turns out to be 5. The distance between those 2 points is 5. And I realized when I looked at this one that the last one also had an answer of 5. Please don't think that every distance formula has an answer of 5. It's strictly coincidence. I'm going to make sure I change some of these numbers around for the next time I do these examples. But the idea here is this. We can use the distance formula to find the distance between any 2 points. And basically where the distance formula comes from is the Pythagorean theorem. That's what I want you to get from that. Are there any questions about what we did here before we move on to something a little bit different? All right. The midpoint formula. The midpoint formula is exactly what it is. Find the midpoint of the line segment between the points negative 2, 5, and 6, negative 3. You don't have to draw a picture of this, but if you wanted to, let's see, negative 2, 5 would be here, and then 6, negative 3 would be here. And if we connected those with a line segment, what would the midpoint be? Somewhere in there. That's what we're looking for here. And the midpoint formula is very logical. So we won't spend as much time on this as we did the distance formula. For the midpoint formula, what we're going to do is we're going to add up the two x values and divide by 2. We're finding the mean of those two x values. And then add up the two y values and divide by 2. We're finding the mean of those y values. So essentially, we're finding the mean of the x's, we're finding the mean of the y's, because we're finding what's halfway. And that's exactly what we're doing, is we're finding what's halfway. So to find the midpoint of this segment, and again, we could name these however we want, but make sure we're consistent. I'm going to make this x1, y1. I'm going to make this x2, y2, and I'm going to find the midpoint of this line segment. And so the midpoint will be, let's see here, x1 plus x2 over 2, y1 plus y2 over 2, and then we'll simplify. Let's see here, negative 2 plus 6, that's 4 over 2. 5 plus negative 3, that'll be 2 over 2. And these came out to nice tidy whole numbers. And we wind up with a midpoint being 4 divided by 2 is 2. 2 divided by 2 is 1. So the midpoint is 2, 1. You don't have to draw a picture, but you might want to just for illustration purposes. But essentially, we're finding the mean of the x's, we're finding the mean of the y's, and that's what gives us the midpoint, halfway between those two endpoints. Any questions about the midpoint formula and how it works? Excellent. Okay. Now for a topic that does sometimes give students trouble. So we're going to be patient and careful as we go through this. Some of the concepts, definitions that we've talked about in our coverage of geometry so far are going to be useful for us when we're given a diagram and we're supposed to find angle measures. The concepts that are going to be most valuable for us are going to be these following ones here. That if we add up the angles in a triangle, we get 180 degrees. Complementary. That's if we have two angles that are complementary, they add to make 90 degrees. Two angles that are supplementary add to make 180 degrees. And then let's see, this one's going to be useful too. Vertical angles, ones that are back to back. Like when we looked at vertical angles, we would say that like this one and this one are vertical angles. They share a vertex, but they don't share any sides. That's why they're called vertical angles, because they share that vertex, but they don't share any sides. They're vertical angles and they're equal. And then last, straight angles have a measure of 180 degrees. Now, we're not going to have to use every single one of these properties every single time. These are basically the properties that are in our toolbox. These are in our toolbox, and we're going to use these tools as needed to answer questions about angle measures. Let's take a look at what it is, the type of structure that we're talking about here. So we're given this diagram. We don't know a whole lot about it. We can tell by looking at it that we've got a right angle over here. That may be given to us in the problem, but it's obvious that we've got a vertical and a horizontal line there. So that's a right angle. And what we're asked to do here is find the measure of angle ABC. So what I'm trying to find is the measure of angle ABC. And one of the first things you'll have to be comfortable with is identifying angle ABC. We start at A, we go to B, we go to C. So angle ABC is this one right here. We're looking for the measure of that angle up there in the corner. And we know, because we're given it, that this angle down here has a measure of 34 degrees. All right, so how am I going to get from there to angle B? Well, I'm not going to go straight at it. Sometimes there's going to be a process involved here where I'm going to have to say, well, wait a minute, I can't get angle B yet. but through a series of steps, I bet I can. And that's going to be our approach. And we look for a path, and I see, well, there's a vertex right here. If I look right here, I have vertical angles. And so what that tells me is that this angle must have a measure of 34 degrees also. Okay. Well, now let's see here. I've got this right triangle here, ABC, and those three angles in there have to have a sum of 180 degrees. And I know that this one's 34, and I know that this one's 90. So I'm going to be able to find the measure of that third angle. The measure of angle ABC plus the 34 plus the 90 is going to have to equal 180. Okay, then. So that means that ABC, and you might not have to write this much down. I'm just being extremely explicit. So ABC plus 100, and let's see, 34 plus 90, 124 is 180. And then just like we've done in the past, when we're going to solve an equation like this, we're trying to solve for the measure of angle ABC. I can subtract 124 from both sides. On the left-hand side, my 124s cancel, leaving me with just the measure of angle ABC. And on the right-hand side, I have 180 minus 124 is 56. And I just found out that the measure of angle ABC is 56 degrees. What I did to get here was I used some things that I know. I used the fact that I know this is 34 and I can see these are vertical angles, so that's also 34. I know this one's 90, and I know that these three must add to 180. And with all that in mind, I can determine that ABC has a measure of 56 degrees. Are there questions about what we did there? Anything you want to bring up or ask before I have you try a couple of these? All right, let's try something. Kind of a crazy looking picture there, and I'll give you some time to draw it. If I were to draw this, I think I would start with those two, just the vertical and the horizontal, and then maybe draw in this diagonal, and then draw the triangle on there. If you're artistic and you don't need my suggestion there, totally fine. You draw it however you want to, but I think that's how I would go to try to draw this picture and get it labeled. We don't have to be in a hurry. In fact, I want to be patient as we go through problems like this. And what our job is here is to find the measure of angle XBH. So you'll have to figure out which angle is XBH and then figure out how you're going to find it. One thing I will say is this 32 right here goes with this angle right down tucked in there. It was just, the 32, if I made it much smaller, it'd be hard to read. So that 32 degrees goes with this angle right here. Even though it is kind of far away from it, that's the angle that it goes with. All right, I'm gonna leave you to it. I'm gonna let you try this one. I'm gonna set up a poll for it, and we'll see how it goes. One thing I will say about these is there's not necessarily one right way to go. You may do it a different way than somebody else and still arrive at the correct answer. There is one right answer, but there may be more than one way to go about getting there, depending on what the problem is. like I said, these can be pretty challenging. So be patient with yourself, be patient and careful as you go through them, and think about those properties that we have at our disposal. You know, um, straight angles, vertical angles, complementary, supplementary, and what do we get when we add them all up in a triangle? Those can be really useful. And also, kind of like um, kind of like a lot of word problems that we did sort of at the beginning of Math 122. Um, try something. You always want to, well, I'm just going to try something and see where it takes me. Maybe the first thing you do turns out not to be the right thing. That's okay. Um, you definitely want to try something. We'll go another 30 seconds on this, and then we'll talk through it together. And I'll give you a chance to practice another one after that. Let's see how we did. Okay, we're spread around on this one. All right, let's go ahead and take our time and talk about this one a little bit. Um, so probably the first thing that I see here, and it may be the same thing you see, it may not be, is I've got a right angle. And if this is a right angle, then so is that. So, CXH is a right angle. With that in mind, and knowing that CXB is 32 degrees, then BXH here, BXH, and the names are very important, this angle here must be the rest of what would get me to 90. Good question, Zara. I'll address that in a minute. So that's got to be the rest of what gets me to 90. And so then I can just do 90 minus 32, and that gives me 58. Now I see that was our most common answer, was 58 degrees. And 58 degrees would be correct if we were asked for angle BXH. But we weren't. We were asked for XBH. Here X is the vertex, here B is the vertex. And so while finding BXH might be an important part of solving this problem, it's not our answer. Now, once we know that BXH is 58, and we can see this right angle here, BHX, we've got a 58 and we've got a 90, and angle B up here that Zara points out, angle XBH, because XBH is the angle that if we go from X to B to H, so that's this one, that's the one we're looking for, that's going to finish off this triangle for us. And so I'm going to have 58 plus 90 plus XBH that I'm looking for has to make 180. Those three angles together will make up the three angles inside my triangle, so they have to add to 180. If anything we're working on, if any of these numbers or ideas don't make sense, please don't hesitate to ask. Now I can add those. 58 plus 90 is 148. And when I add that to whatever XBH is, I've got to get 180. I'll subtract 148 from both sides and find out that XBH has a measure of 32 degrees. So we used the 32 we were given and the idea that this angle here would get me to 90 degrees to find out that that was 58. But be careful and make sure you find the angle measure you're being asked for. Zara asked an excellent question there. How come it says find the measure of XBH and not just B? And she's right. We could absolutely call this angle B if we wanted to, because there's no other angle coming off of it. What we wouldn't want to do here is say angle X for anything, because angle X could mean this one, or this one, or this one, or this one, or this one, there's a whole bunch of angles on there that have X as a vertex. In this case, there's only one angle on here that has B as a vertex. So if we wanted to call that angle B, that would be completely appropriate. I think I went with the XBH to sort of emphasize our naming idea here, that if it's called XBH, it goes from X to B to H, and so that's the angle we're talking about. But you're exactly right, Zara. If we called that angle B, it'd be the exact same one. Try one more, similar to this. Find the measure of angle GXE. Same picture. Now we're looking for angle GXE. I'm going to set up a poll for it and let you try it. I don't think these are easy. I think they take a little practice, and you have to be sort of patient as you work through it and say, okay, what is it? How am I going to get there to answer this one? And then kind of do it one step at a time. We're not going to be able to go straight to the answer very often. We know there's a 90, we know there's a 32, we know there's a 40, and we may be able to, we're going to have to be able, those are the only things we know. So somewhere in there is our starting point to try to figure out what it is we're going to do to get the measure of angle GXE. And I kind of see two really good ways you can go about this one. Either way works just fine. Let's go another 30 seconds and then talk about it. Yeah, let's take a look. Okay, we have strong agreement here. I don't know that there's a ton of confidence in that agreement, but we do have agreement. So let's take a look. So we're after measure of angle GXE. First thing we have to do is figure out which angle that is. And that's from G to X to E. So it's this angle right here that we're looking for. That's the one we're looking for. I see two different ways you could go here. The way that sort of jumps out at me first is this. I've got this 90-degree angle here, and this is 40. So that means that this angle here, CXF, must be 50 degrees. And then when I look at CXF, wait a minute, if I do this, CXF and GXE, the one that I'm looking for, those are vertical angles. So if CXF is 50, then GXE must also be 50. And so GXE is 50 degrees, and that's it. We didn't have to do much calculation there. We just had to use the vertical angles idea. The other way I could see going about this one would be at first saying, okay, well, the first thing I happen to see here is that if I draw this 40-degree angle and this angle over here are vertical angles. They share a vertex, they don't share any sides. Those are vertical angles, so this is 40. And if I've got a right angle in here, then this is also a right angle. So this 40 plus whatever this is make a right angle. So whatever this is, GXE has to be 50 degrees. Either approach gets you to the same answer there. It's kind of just whatever you happen to see first is going to be the path that you take to get there.